Ever send like a huge file and just, wished it would hurry up, or
Mhm.
waited for a website to load tapping your fingers impatiently?
We've all been there.
Well, imagine that, but like on a scale that would make your head spin. We're talking about Google-sized data centers where like every fraction of a second counts. And that's where things like data compression, shrinking those files down becomes absolutely critical.
What's fascinating is how this isn't just about saving space anymore. It's about keeping those massive data centers humming along smoothly.
Right, right.
We're diving into a research paper by some Google engineers, and you're not
That's,
going to believe this.
mm-hmm.
They found that almost 3%, 2.9% to be exact, of their entire data center's processing power
What?
is dedicated to just compressing and decompressing data.
Okay, let's unpack this. 2.9% might not sound like much, but when you're talking about Google's scale, we're talking about enough energy to power a small city, right?
Precisely. It's a massive amount of resources.
Yeah.
And that's what makes their deep dive into this so interesting. They started looking at the types of compression algorithms, the tools they use to shrink all this data, and found that it's like having a garage full of sports cars, but only ever driving in first gear.
Okay, I'm intrigued. Break this down for me.
So they categorize these algorithms as heavyweight and lightweight. The heavyweights, algorithms like ZSTD, are like those industrial strength compactors. They can really squeeze data down to a fraction of its size, but they take more time and processing power. Then you have the lightweights, algorithms like Snappy, which are designed for speed. They're faster, but they don't shrink the files quite as much.
A classic trade-off. So, what's Google using?
You guessed it. They're mostly relying on the lightweight, speedy algorithms, even though the heavyweights could theoretically save them a lot more space in the long run.
It's all about that need for speed, huh?
In the data center world, milliseconds translate to real money. Every tiny fraction of time saved adds up. But then they asked a fascinating question. What if we could make those heavyweight algorithms faster?
Here's where it gets really interesting. This is where the idea of specialized hardware comes in, right?
Exactly. They started exploring this concept of a dedicated piece of hardware, a chip specifically designed for compression and decompression, which they call a CDPU, or a compression-decompression processing unit.
So like a graphics card, but for making files smaller.
A good way to think about it. But just like you wouldn't put a graphics card in your shoe, the placement of this CDPU within the system is just as important as its design. Do you put it right next to the main processor? On a separate chip nearby? Or off on its own, connected via PCIe like a high-performance graphics card?
So many options, so little time.
They ran simulations to figure out the ideal setup and found that it actually depends on the task. For smaller, simpler compression jobs, those quick, snappy tasks, keeping the CDPU close to the main processor is best, minimizing travel time for the data. But for those heavier jobs that ZCV excels at, having it on a separate chip or even connected through PCIe might be the way to go. It all comes down to striking that balance between speed and efficiency.
It's like finding the perfect parking spot for your compression needs, depending on whether you're running a quick errand or settling in for a long stay. So we've got these CDPUs, these specialized chips for crunching data down to size, but it sounds like where you put them is a bigger deal than I ever imagined.
Absolutely. And it gets even more nuanced when you start looking at the compression algorithms themselves. Remember those heavyweight ZSTD algorithms we talked about, the ones with the potential to really shrink things down?
Yeah, like choosing the highest compression level on a zip file.
Exactly. But here's the thing. They discovered that Google is mostly using ZSTD at a very low compression level. It's like they've got this supercar, but they're only ever driving it in first gear.
Wait, really? Why would they do that if it means missing out on all that extra compression?
Because even with those lower settings, ZSTD can still be slower than the lightweight Snappy. And in the data center world, remember, time is money.
So they're sacrificing some storage space to save on processing time. Makes sense, but it seems like there's a huge opportunity for improvement there.
You hit the nail on the head. They crunched the numbers and found that bumping up those ZSTD levels could improve their compression ratio by almost double.
Yeah.
Imagine the impact that could have. Less storage space needed, potentially even less bandwidth used to move data around.
Well, this CDPU, this specialized hardware, could be the key to unlocking those higher compression levels without sacrificing speed.
It's a huge piece of the puzzle.
Oh.
But remember, it's not just about raw power. They also had to consider the size of those data chunks being compressed. And here's where it gets really interesting. They found that most of the compression tasks, especially for Snappy, involved relatively small pieces of data.
Makes sense, right. It's not like we're always dealing with one giant file. Data is constantly being generated and transmitted in smaller bits and pieces.
Precisely. It's like the difference between packing a moving truck versus organizing your kitchen drawers. You need different strategies for different scales.
So they need a CDPU that's not just powerful, but also nimble enough to handle those smaller, more frequent tasks.
You got it. And they went even deeper, looking at the types of data being compressed. Turns out a large portion of it was related to something called protocol buffers. Ever heard of them?
Vaguely. It's a way to structure data, right?
Right. Think of it like a universal language that different applications can understand. And compressing these protocol buffers is a huge part of what's going on in Google's data centers.
So you're saying they should design these CDPUs specifically for protocol buffers?
It's tempting, but it could create problems down the line. Technology changes fast. What if protocol buffers become obsolete? Or what about all the other types of data that need compressing? They need a solution that's adaptable for the future.
So what's the answer? How do you design a CDPU that's both specialized and flexible?
That's the million-dollar question, and their research points to a few key insights. For example, they found that the physical placement of the CDPU, well, let's just say location, location, location applies to data centers too.
Okay, so we're back to location. They're talking about where the CDPU lives inside the system, right?
You got it.
Yeah.
It's all about proximity. They found that for those smaller, faster tasks, like what you see with Snappy, having the CDPU directly connected to the main processor was the way to go. It's like having a dedicated assistant right there in the room, no need to send files back and forth across the building.
So cutting down on those data commutes.
Exactly. Every little delay adds up. They even tested having the CDPU on a separate chip, but still physically close to the processor.
How'd that work out?
It was good middle ground for the heavier compression jobs, offering a good balance of speed and flexibility. But for those quick, snappy tasks, nothing beat being directly plugged in.
Fascinating. It's amazing how these tiny details can make such a big difference in the data center world.
Absolutely. And remember that history window? We talked about the CDPU's short-term memory for data patterns. The size of that also played a key role.
Right, because a bigger history window means better compression, but also more cost and complexity.
Exactly. For Snappy, they found that even a small history window, we're talking 2PB, could handle data almost 10 times faster than a typical processor core. That's like going from a bicycle to a race car.
10 times faster. That's incredible.
It is. But for Ziz today, those heavier jobs, they needed a larger history window, about 64K to reach its full potential. Even then, it was about 4 times faster than the processor. It highlighted this trade-off. Do you prioritize speed for certain tasks, even if it means sacrificing some compression for others? Or do you aim for a balance, accepting slightly slower speeds for those heavier jobs to maximize overall compression?
So choosing the right tool for the job, but in this case, the tool is a tiny piece of hardware.
And the best choice depends on the specific needs of the data center. There's no one-size-fits-all answer.
What's really cool is that they didn't just theorize about all this. They built custom benchmarks based on real data from Google's data centers to test it all out.
And even better, they made those benchmarks open source. That means other researchers, even other companies, can use them to explore these concepts and drive innovation.
It's like they're sharing the map to a more efficient digital future.
I love that analogy.
Who knows what breakthroughs we might see? Faster phones, quicker downloads, all thanks to a deeper understanding of how we shrink down those ones and zeros.
It makes you wonder, what will they think of next?
Right. Well, that's all the time we have for today's deep dive. But if you want to learn more about this fascinating research, be sure to check out the show notes for links to the paper and those open source benchmarks. Until next time.